Welcome students. Today we are going to see about electric boundary condition. In that we will see dielectric boundary conditions today. So the electric field exists in the region that consists of two different dielectrics. So assume there is a region. So this may be the region. So there are two dielectrics. So in the region 1 take the dielectric value as epsilon 1 and region 2 take dielectric value as epsilon 2. Corresponding E1 is the electric field intensity in media 1 and E2 is the electric field intensity in the media 2. So from according to our definition we can write total electric field intensity can be resolved into tangential component as well as normal component. So E1 equal to E1t plus E1n. Similarly E2 is equal to E2t into E2n, that is tangential component of electric field at medium 1 plus normal component of electric field at medium 1. So tangential component of electric field at medium 2, normal component of electric field at medium 2. So assuming now I am going to derive the boundary condition. For that I am going to assume a small elementary closed path, this path A, B, C, D, a small elementary path. So now I am going to move from point A to B and B to C and C to D, again D to A, by applying the corresponding boundary condition. So now I am moving from A to B. So what is the length of A to B? It is delta W. So delta W into ET1. So it is a tangential component. So it will be E1T. So E1T into delta W. Similarly, so from where I'm moving to B to C, so you are crossing the border, that is boundary. So in medium 1, the total height between B to C is delta H. So you can take delta H by 2 into En1. Similarly, delta H by 2 into En2, that is En1, En2, because it is a normal component, perpendicularly you are moving. So normal component into height, so that height is delta H by 2. You get to divide into superpolymers. So here minus n, because the closed path assuming and the moving point both are in opposite direction. So you can take it as minus. Similarly, when coming to second C to D, so you are moving in this direction. So C to D, again length is delta W into E to N. So it is second quadrant, so E to T. And then similarly for D to A, E to N delta H by 2 plus E1N into delta H by 2. So here you take, so tangential component of electric field is equal to magnitude of tangential component of electric field. Similarly delta component also magnitude. So if suppose the value of delta H is very small, then we can neglect it. So they neglect all the terms delta H in the equation, you will get 0 is equal to E1T minus E2T into delta W. So that is E1T is equal to E2T. From this you will state the statement, you write the statement as tangential components of electric field are same on both the sides of the boundary, that is E1T is equal to E2T. So tangential component of electric field at medium 1 is equal to tangential component of electric field at medium 2. So that means the total tangential component of electric field has no change on the boundary. It's said to be continuous, or you can say it is here, it is continuous across the boundary. So it's the boundary condition number 1. So it will be continuous across the boundary, or it does not have any changes while crossing the boundary. So the tangential components will be same. Next, coming to second boundary condition. So according to our definition we can write the formula for electric flux density D is equal to epsilon into E. So that you can write tangential component, that is normal value plus tangential value. So again the formula for D is equal to epsilon by E. So E is equal to epsilon. So what we proved, E1T is equal to E2T. So E1T you can write D1T by epsilon 1. E2T you can write D2T by epsilon 2, that is tangential component of electric field at medium 1, tangential component of electric flux density at medium 2. So we can write D1T by epsilon 1 equal to D2T by epsilon 2. Actually here epsilon 2 we can take, which is the medium number 2, so epsilon 2. So from you look at, so the value of D will be dependent upon the epsilon value. So for if the medium has highest epsilon value, so automatically there should not be a continuity. So D2 undergoes some changes across the boundary, that is interface between the two surfaces. So automatically it should not be a continuous one. So the value of electric flux density is discontinuous at the surface. So this is the our second boundary conditions. So remaining we will see in next class.